Well, welcome back. We're in section 5, and before I really get started, I want to make a special announcement that we're going to be skipping sections 3.6 and 3.7. So after this lesson, we'll be jumping to the end, 3.8, and that will complete our chapter 3. And then we get to my favorite part, chapter 4. But in the meantime, let's look at some business and economics applications. And we're going to solve a few problems here, some sample problems, of course. And at the end, we're going to look at some basic business terms and formulas. Most of this you've looked at before, but it's a good idea to review. So here we go. All right, let's get right with the examples. We're talking about revenue this time, and we've got a model. This model, and if you wanted to be a little more mathematical about it, you might make this R as a function of X, or R is the revenue in dollars, and X is the number of units produced and sold. The question is, at what production level, that's X, will we get a maximum revenue? So this should be pretty easy, right? I wonder if you could do this by yourself. Why don't you give it a try? It might be fun. If you can do it, that'd be a great plus. Well, even if you took a break and tried that, you're back. Let's move on. So, sketch of the revenue function. What's it actually look like? Well, this is where a graphing calculator can be really handy, and it can help guide you through the process. Here's what the revenue function looks like, and we can see roughly where the maximum is. We're going to double check this though. So here's the primary equation. We don't have a secondary equation. We've only got one variable here, just all x's. That's good. And our revenue, of course, is the main or the primary. The feasible domain, remember, X is the number of items that you're producing and selling, so you can't have a negative number of X's. And the domain is up to 546. You can tell that by looking at the x-intercepts. What does that mean? Solve this, or excuse me, factor this, take out the x, and then factor what's inside, set it equal to 0, because y equals 0 gives you an x-intercept, remember? To maximize the revenue, find the derivative, of course. You've been here before. That should be child's play by now. Find the critical numbers. In other words, take the derivative, set it equal to 0. Factor it. Another way of doing this would be dividing this by -3, and then factor. That gives us two solutions to this equation. 350 and -50. But -50 isn't in the feasible domain. Throw that out. So this is our only critical number. Here again is the function. You can see the 350 is at the maximum for the revenue. Now we're going to take a look at something a little bit different. I've mentioned this several times, the average cost function. And Something very similar can be done for average revenue or average profit per item. This is the symbol for average cost. You have that bar across the top of the C, and that just means you take the C for the total cost function, divide it by number of items, which will be X, and you've got your average cost function. So C is the total cost function, X is the number of units produced. There is our cost function, total cost function. We're starting with that. We want to minimize the average cost per unit. Well, that makes sense, right? Regardless of what we're producing, we want that cost per unit to be low. And this way we can take a look at it from sort of a mini viewpoint or a micro viewpoint. See how we can keep the cost in each of those items as low as we can. Since this is total cost, and we're talking about average cost, our primary equation looks like this. So you take this, put X on the bottom, there we go. There's our average cost function. Next, divide in X into each of those terms. And you know we're going to differentiate next. The middle term, of course, will give us a 0. The feasible function, the X has to be greater than 0 because you can't produce a negative number of units. What's a negative number of TVs, for example, or a negative number of lights? Pretty silly, right? But when you're talking about the X's, it's good to know what X's are available when you're working with it mathematically. So here's our derivative. And what are we going to do next? Find the critical numbers. Set that equal to 0. Solve for X. Part way down. A little bit closer. There's X squared. Take the square root of both sides. You get 2 answers, but remember our feasible domain. Can't have that negative. We don't produce negative numbers of things. Sketching the graph. Here's our 2,000. That minimizes our average cost per unit. And last of all, this has been pretty short, but I got a few things to look at. X usually represents the number of items produced or sold. P, price per unit. Notice that this is a small p. R for revenue. C for total cost. These are all totals. These 3, remember, are totals. This is average for cost. Our marginals, marginal revenue. Notice these are next to each other horizontally. Total cost, marginal cost. Profit, marginal profit. And a couple of things to look at. Demand function. Demand function usually looks like this. Smaller the price, or the higher the price. If you go look back here, higher the price, the smaller the demand. This is the x-axis here. This is the P. Higher the price, less demand. Lower the price, higher the demand. That makes sense. Give it 1 minute's thought and you'll have that down. Revenue. Now we're not going to talk about elastic demand. It's one thing we're going to leave out. However, it has to do with price and demand relationships. If something goes up in price, what happens to demand? Does it go down? and vice versa? Or are they about the same? Anyway, we're not going to talk about elasticity. These are a couple of functions that we can look at. Cost function. Here's our fixed cost, because even if we produce no items, there's certain fixed costs like insurance or heating, lighting, that sort of thing. And then depending on how many items we're producing, that cost goes up, because you can't produce something with no cost, at least not normally. And profit function, the break even is where revenue equals cost. Two ways of looking at that, remember? You can say break even is when profit equals 0, but profit equals revenue minus cost. So if this is 0, then 0 equals R minus C, or R equals C. Two ways of looking at the break-even point. This or this. Each translates to the other though. Well, that's it. We are finished. And we're ready for the test for chapter 3. And then we'll move on to exponentials and logarithms and have a little bit of fun on the way. You keep smiling, and I'll see you in the classroom. Bye-bye.